Swayam Prabha. Digital India. Educated India.
Yesterday we discussed the concepts of arrays and what it took to, from a system perspective, what are the benefits of using arrays in the context of millimeter wave systems, what a radar system requires, what a communication system requires. And now, so that was sort of a top-down approach, and today we'll do a bottom-up approach where we will start looking at transistors, passives, the basic building blocks that we have, and then we'll go back up to look at array architectures and then come back down again to start building circuits using these components. So we'll begin by looking at transistors and then we'll do passives. So I've included a list of references that have been used in putting together this material. This is of course a subset. There are other books as well. For example, Posar's Microwave Engineering is a book that has been useful as well. But these are, interesting concepts that have been covered well in this material. So if you want to go deeper, happy to refer other material as well. We'll first begin by reviewing S parameters. Right. General problem that we face at high frequencies is that we want to build complex systems that we want to characterize. And in the last lecture, we talked about lumped versus distributed systems and the trade-offs of modeling them, right? So let's say that I have a pretty complex system where I have an amplifier. I may have a power divider that is then splitting this into two parts. I may have some interconnect that then routes this signal over. I may have some sort of bandpass filter, right, that is passing signal through, and then again I have some cable connected to an amplifier going. And I might have a similar network over here, right? And my objective is I want to be able to characterize transfer functions for this whole network, right? So I can, of course, consider this in an arbitrary fashion, right? And consider some network which has what we call ports, right? Places where we are interested in observing, applying input or observing the response, right? So let's say that I have a 3-port network. Of course, you could generalize this to n. So at low frequencies, when we are generally analyzing networks, we use Z parameters, for example, right? And that just links V1, V2, V3, right, through a matrix that we develop, right? As a function of the currents at each port, right? And this works fine, right? So this network is can be described this way. So if we want to find out any particular voltage based on these current excitations, we can find this out by using this matrix. But how do we determine this matrix in the first place? You can do it in various ways, but a simple way in which we try to do this is, if I want to find out what Z11 is, I consider what V1 is when only I1 is applied, and for that I need I2 to be 0 and I3 to be 0, right? And then I'm able to get this Z11. And I can do this for every other parameter. But this basically is assuming effectively that I'm able to create an open at port 2, right, and port 3, right? That would be the measurement, right? That I'm able to apply some test voltage here, and I leave these two ports open, and I'm able to measure the current going in. But there are a couple of problems there. Firstly, in a real network when I'm trying to measure, there might be capacitances, so it's very hard for me to guarantee a perfect open. Or if I was trying to measure Y parameters, the equivalent would be that I have to make a short. But my short will not be a perfect short. It might have an inductance or something like that. So now I have a situation where it is difficult for me to measure these parameters, right? And similarly, I may have a situation where yesterday we discussed that then even on that port, as we are trying to measure, right? So we have that port, let's say that 2 is open and 3 is open, right? And I'm trying to measure on port 1. Imagine a simple system where all we are trying to measure is a load resistance ZL, right? Then we typically would know that Z11, it would just simply be V1 divided by I1, it would be ZL, right? But when I'm trying to measure it, I'm not able to access this point exactly. So then let's say that I have some sort of interconnect going to ZL, right? And this interconnect has some characteristic impedance ZC, right? I end up then with a situation where what I see over here, right? Let's call it Z11 now that I would be measuring, right? So I'll call it Z11 measured, right? So Z11 measured is going to be a function of ZL. It's going to be a function of this length of interconnect. It is going to be a function of the characteristic impedance. It's going to be a function of the frequency, right? It's going to be the function of the velocity in that interconnect, right? So effectively, it just becomes hard for me to measure. So I now can think about basically instead of doing this, right? I start thinking about characterizing networks in another way, where I start the same concept of having the multi-port network, right? But now I'm basically going to say that the voltage at port 2 is a sum of two voltages V2 plus V2 minus, and similarly the voltage at port 1 is a sum of two voltages V1 plus V1 minus, so on and so forth. And similarly the current at port 1 is I1 plus minus I1 minus. So there is basically, I think of some current coming in like this, a current wave going out like this, right? And in this scenario, as I basically define a new set of parameters where I say that the S parameter network is V1 plus, V2 plus, so on and so forth to Vn plus, right, is on this side. And I should just take this over again because since I'm defining the S minus is on this side, right? And I have this parameter which is V1 plus, so on and so forth till Vn plus, okay? So I am basically thinking of the voltage at any node being the sum of a forward voltage wave and a backward voltage wave. So there is a forward voltage wave traveling in this direction, a backward voltage wave traveling in this direction. So the voltages at any point, they add up, right? And the currents, the direction matters. So you basically get, in my notation, I1 becomes I1 plus minus I1 minus. So I'm thinking in my network that there is a forward wave of voltage and there's a reflected wave of voltage, a forward wave of current and a backward wave of current, right? And why do I do this? Well, in this scenario, I find that if I want to measure V1 plus by V1 minus by V1 plus, right? And that would be S11. I need to basically make sure that V2 plus, V3 plus, etc., Vn plus are equal to 0, right? That becomes my objective in the measurement. And I know now that I can basically define this concept of reflection, right? Where whenever there is a certain load and I am connecting to it with let's say a transmission line which has a characteristic impedance ZC, right? And I think about the reflection here, I can basically show that my reflection, which I'll call gamma L, right, is basically ZL minus ZC divided by ZL plus ZC. And this reflection coefficient basically is the ratio of, if I call this direction wave V1 plus and this direction wave V1 minus, I basically get V1 minus by V1 plus to be ZL minus ZC by ZL plus ZC, right? This is gamma L. So if I want basically for the reflected wave to be 0, right? So for the reflected wave to be 0, I need to make sure that ZL is equal to ZC, right? So what this is basically saying is that in the context of that measurement, right, if I think about port 2, that there is, I am defining in port 2, remember V2 plus this way and V2 minus this way. What I'm saying is that if I terminate this port in an impedance that is exactly ZC, right? Let's say I define everything to be based on some characteristic impedance ZC, then I will not get any, I'll not get any reflection back, because this wave V2 minus will go here, right? And this reflection will be 0. So I can ensure that V2 plus basically doesn't exist by terminating the port in ZC. So now my measurement becomes a lot easier, because all I'm doing is I'm taking my port and I'm taking the port 2, for example, and it doesn't matter how much, we will see shortly that it doesn't matter what length of transmission line, whatever network that I use here, right? Sorry. That whatever network that I use here, it doesn't, so as long as I terminate this over here, right, in ZC, then effectively I'm basically ensuring that when I'm measuring V1 minus divided by, is this color not visible here, right? Sorry. So when I'm doing V1 minus divided by V1 plus, I'm basically making sure that, that I'm measuring S11, because I'm able to ensure the condition that V2 plus is 0, V3 plus is 0, so on and so forth, because I'm terminating all of those ports, right, in the characteristic impedance. So this has the same ZC transmission line and I'm able to terminate it, right? So effectively then S parameters are a very useful measurement tool at high frequency, because you can now measure S parameters by ensuring termination. And this is a very high level overview of S parameters. I'm sure that you have studied it before, but there is also a view of S parameters as power, because when I'm thinking about, for example, a forward wave going which is V1 plus, right, which has a magnitude V1 plus, and let's say that this has I'm defining everything with a certain characteristic impedance, then the power is a function of V1 plus squared divided by ZC, right? So effectively, when I am considering V1 plus, right, I can think of this also as forward waves of power going and back, and power getting reflected back, right? But it's all voltage waves traveling and voltage waves reflecting back, but the power is proportional to the voltage squared. So you can think as power going into your network and power getting reflected back from your network. And what you do when you put a termination here which is matched to the impedance is that you are absorbing the power, so none of the power is reflected back, right? So making S parameter measurements is a lot easier at high frequencies than Z parameters, right? And there is really no uniqueness to this, right? Because remember, we say that the voltage at any port K is Vk plus Vk minus, right? And the current at any port K is Ik plus minus Ik minus, right? And we have the relationship that Vk is this, right? So now what we basically can say is that let's write our normal z parameters, right? So V would be z times I. So basically V plus the matrix V plus so all of the V pluses plus all of the V minuses are z times I, which is z times V plus divided by z naught or zc, whatever we call the impedance that we are working with, right? And so now I can basically take this to the same side, and I can effectively see that so then let's do it this way. So z by z naught minus the unity matrix times V plus is z over z naught plus the unity matrix times V minus, right? And so if I'm basically characterizing V minus as a function of this, then this becomes V plus times z over z naught minus u divided by z over z naught plus u, right? So this basically says that your to be consistent with matrix notation, I'll move it to the other side, right? So then I'm basically saying that my S parameters z over z naught plus u inverse times z over z naught minus u, right? So there is a one-to-one correspondence between the z and the S, right? So we use S because it's sort of easy to measure. You can always analyze your network when you analyze it in Z or Y and then convert it back to S. You can measure S and then convert it back to Z and Y if that helps you on the analysis, right? But the Z parameters, the S parameters are not some network parameters that are specific to high frequency or some unique set of network parameters that are different from the others. They are just another way of representing the voltage and the current, which are easy to measure at high frequency, because enforcing the conditions that are required to measure it are easier at high frequency than enforcing the conditions for voltage and current, right? So that's the only difference between the two. So when you say that you have broadbands, opens and shorts available, it still, we ask the question, where do you apply it, right? So if you look at the broadband short that is available, let's say that you're trying to characterize a network, right? Just a simple two-port network. And I need to place the short right over here, right? But the broadband short that you have available now is going to have some electrical delay associated with it, right? And then in reality, even on the measurement side of it, you have an issue, right? Because you are not able to measure the voltage and current right at this node, right? What does that imply? That implies being able to bring a voltmeter or ammeter right there and measuring it. But any cable that you have in your voltmeter is going to change the voltage. We saw that if along that line that I measure, right, there is a certain voltage, there is a delayed voltage over here, right? Yeah, I mean, stand-in waves are one phenomena, right? But effectively, you want to know, and don't think of this only as a real resistance. There is a complex resistance here. So there is a phase between the voltage and the current. So you want to be able to measure the voltage at this node, and you want to measure the current exactly at this node. It's not possible at high frequency for you to access that particular point without the measurement setup itself impacting what you measure. So measuring S parameters, you can measure it without your network impacting it, right? So it's just a lot easier to measure S parameters in your system. So from a network perspective, we generally at high frequencies, and particularly because early on work at these frequencies happened with discrete devices, right? So you generally start describing them in S parameters. But on chip, it's fine to use Y or Z parameters when you're analyzing, but right at the end, you should know when you're measuring, you're going to be measuring S. So you should be able to design with it as well. And in the end, whether you design with S, Z, or Y, it's ultimately the same network. So it doesn't really matter what you use. The other concept that I wanted to quickly review is conjugate matching or power. The idea here is, again, we can analyze it even with simple Z, right? That we have a source which has a certain Zs, right? And we have a load which is ZL, right? And what we would like to do is transfer power from this source into this load, right? So we know that the current is going to be Vs divided by Zs plus Zl, right? And we know that the power that will be in the load will be I squared times I guess IRMS squared times RL, where RL is the real part of the load, right? So we can say, for example, that the load is RL plus JHL and the source is RS plus JHS, right? And in this scenario, what we end up with is that the power transfer to the load is, assuming the RMS is a half, right? It's Vs squared divided by Zs plus Zl squared times RL, right? And this works out to Vs squared times RL divided by this is Rs plus RL squared plus Hs plus HL squared, right? So if we want to maximize the power that we are sending into the load, what we see is that Hs plus HL must go to 0. So this implies HL must be minus of Hs, right? And we can basically see that there's RL in the numerator, Rs plus RL squared in the denominator. And we can basically show that the power will be maximized when Rs is equal to RL, okay? So this basically tells us that for maximal power transfer, right, this implies that HL is minus Hs, right, RL is Rs, which basically implies that we are asking for the load to be the conjugate of the source impedance, right? And this is what we call conjugate matching. Notice that conjugate matching is not reflection free matching, right? if I really wanted to make sure that there were no reflections back and forth, I should make ZS equal to ZL, right? Because then ZL minus ZS by ZL plus ZS would be 0. But in conjugate matching, there are reflections, right? But these reflections sort of cancel each other until to the you get to the point where you are basically transferring the maximum power into the load when ZL is ZS conjugate, right? So conjugate matching and reflection-free matching are two different things. Does this make sense? Okay. So this hopefully we reviewed a couple of concepts that that will help us going forward, right? But what we like to focus on is the transistor itself, right? And first we sort of think of the transistor, we'll basically characterize it, let's say as a two-port, right? Where there is a input port and there is an output port to this transistor, right? And the job of the transistor hopefully is to you are trying to get some gain out of this transistor, right? Now the gain you can think about different ways, right? You can think about gain as voltage gain, where basically you are saying that you want the whatever be the voltage at V2 by whatever be the voltage at A1, you are getting some voltage gain out of it, right? And this is a traditional way that we define analog amplifiers and we amplify. You can also think about gain as power gain, right? Where basically you are saying that P out minus P in is some gain that you have, that is basically you are applying, so you are applying some DC power into your transistor, right? And what is happening is that it is using the DC power to take the input power and increase it and give you some higher output power than what was put in, right? Notice that for getting voltage gain, you don't really need to have power gain. As an example, right, we have a transformer, right? Let's say this is a 1:n transformer, right? You can get voltage gain from input to output, right? So this will be V1, this will be N times V1, right? So you can get voltage gain. But what also happens is that this is I1 and this is I1 divided by N, right? So if you look at the product of V and I, it stays the same, so there is no power gain, right? So in circuits and in papers, sometimes people will talk about passive gain, right? And by passive gain, what they mean is voltage gain. You can get voltage gain using passive networks. Broadly speaking, you can think about some passive network, right? And looking into this side, let's say the impedance is Z1, right? And you are applying some power into the device, right? Which is Pn, right? So V1 squared divided by Z1, real part of Z1, let's say, is going to be proportional to Pn, right? And then on this side of the network, let's say that you have the same Pn, right? But this is V2 because this has a different impedance. So let's say this is proportional to V2 squared divided by real part of Z2, right? So all I need to do is make sure that this resistance is larger than this resistance, then this voltage will be larger than this voltage. I will not have power gain, but I will have voltage gain. Does that make sense? So you can clearly see that passive gain can be obtained by impedance transformations, right? But for power gain, you really need to put some DC power in order to get P out that is greater than Pn. So we usually want to use our transistor to accomplish that, right? And we like to calculate how much gain can we get from the transistor and or from a different technology, what are the upper limits of the gain that we can get, right? So we define for a 2-port, right? We basically want to look at what is the gain that, let's say that I have a source. Again, I'm going to, for now, explicitly write Bs with some Zs, right? So I have some source, right? And I'm trying to drive a load, right? And I basically want to maximize the power transferred from the source to the load, and I have put this 2-port in the middle, right? I know that if I directly connect the source to the load, I will get some power transfer, which we just computed, right? But I'm hoping that by inserting this 2-port in the middle, I can amplify this power transfer, right? So I apply this metric that, okay, what is the power that I am able to dissipate in my load divided by the power that is available from the source, right? And logically, it seems that, I mean, you can, Posar and Gonzalez have derivations in terms of S parameters for all of this. We'll just take an intuitive view here. But logically, it seems like what should happen is that I should make sure that I extract as much power as possible from the source, right? So I should conjugate match the port and the source at the input. And on the load side, I should again conjugate match these two so that I'm able to extract as much power as I can from the output, right? So this is sort of maximized. So my gain is maximized when I am able to make sure that I am conjugate matched at input and output, right? Let's define a few things before, right? So this is Zs, and looking in here is Zn, right? And this over here looking in is Z out, and this looking in here is ZL, right? And what we can basically do is we can represent all of these impedances in terms of the reflection coefficient that they have with respect to a characteristic impedance Z naught. But just to explicitly write it out right now, we can say that ZL must be Z out star, right? So given this scenario, right, what we try to use is this concept of reflection coefficient, right, where we'll basically write the Zn minus Z naught by Zn plus Z naught as gamma in, right? Zn minus Z S minus Z naught divided by Zs plus Z naught as gamma S, Z L minus Z naught. So I'm normalizing everything to Z naught. Oh, sorry, so that was gamma L. And this is gamma out, right? So then I basically write my conditions as gamma L is gamma out star, and gamma S is gamma in star. This is what I need to do to match the load, right? But to rewrite that equation here on this page, just so that we have it available, right? Once we have this gain that we want to maximize, right? What we see is that we can show that basically the gamma in that you see in the network, right? This is the 2-port. It is terminated in the ZL, right? It's being driven by ZS, right? And what we basically see is that the Z in over here that we see, right? A Z in or gamma in, however we characterize that impedance, right? What we see over here is that if I think about this in S parameters, right? You can do this in other parameters as well, but the principle stays the same, that you see this as S12 S21 S12 gamma L divided by 1 minus S22 gamma L, right? And you see gamma out, which is the impedance that you see over here, as S22 plus S12 times S21 gamma S divided by 1 minus S22 gamma S. So what we are basically seeing here is that gamma in depends upon gamma L, or what we see on this side of the port depends upon how we load it, which makes sense. And the impedance that we see looking in this way, this is so Z out or gamma out, what we see over here, right? It depends upon what the gamma S is, right? But remember that in order to optimize, we want gamma S equal to gamma in conjugate, right? So we are basically now saying that to expand on that equation, we want S11 plus S21 S12 gamma L divided by 1 minus S22 gamma L to be equal to gamma in, but we want gamma in to be gamma S conjugate. So this is gamma S conjugate, right? And we need S22 plus S12 times S21 gamma S by 1 minus S22 gamma S, right? We need this to be equal to gamma out. So what you end up with over here, that this should be equal to gamma out, or it should be gamma L conjugate, right? So this is a set of equations in gamma S and gamma L, right, which you need to solve to find out what you get. What source and load impedances uh, uh, you should will basically give you the best gain in the system, right? So we now there isn't a guarantee that these exist as realizable impedances. Okay, so they may exist or they may not, right? But there are I'm not going to write out all the equations in order to solve this, right? But you can basically apply this solution, and you can I think it's important to at least see the form of these, where you can basically see that the best source termination is going to be B1 minus, I'll just write down this. and okay. So if you solve in those two equations to find out what are the best source and load impedances, you end up with these equations to find out what they are, right? And I just want to highlight this particular term because we will use it later as well, right? This S11, S22 minus S21, S12, right? But this is like the determinant of the S parameter matrix, right? But what does this intuitively mean, right? So this intuitively, what we are trying to say is that I have this two port, right? If you want to get the best gain out of this two port, right? What you need to do is make sure that the source that is driving it has a certain source impedance gamma S max, and the load that it is seeing is the best load gamma L max, right? And if you are able to guarantee that, then this two port will provide the maximum gain that it can, right? That's basically the logic. Now, it might be true that based on the previous equations, the gamma S that gives you the best load may not be a realizable, gamma S that you get may not be a realizable gamma S. The gamma L that you get may not be a realizable gamma L, right? That's fine. But these two, if you are able to achieve, then that will work. So then from a design perspective, what we can do, if they do exist, if they are realizable, is that I have some, let's erase this, right? So what I can say from a design perspective is then I take my transistor, right? And I know its two port parameters, right? There is an actual load that I have that I'm trying to drive, right? So what I do is I build some network over here, right, which takes this load and makes sure that we can call this the matching network, right, which takes this ZL and moves this to the equivalent of gamma L max. So I have some source, right, and I am basically able to have another matching network that over here moves this so that I get gamma S max, looking in this way, right? So then this would seem to make my amplifier design fairly systematic, right? So I take my amplifier transistor, I characterize its S parameters. Once I know its S parameters, I know what is the impedance that I need to get here and what is the impedance that I need to get here. I know what my source impedance is, I know what my load impedance is. So my job becomes to design this matching network and this matching network on the source and load side. And then I put the whole networks together and I should get the best gain that I can get, right? So does this approach work? Yes, right? It works in practice. You can run a simulation in Cadence, for example, of your device, find its S parameters, and there are actually programs that once you give it a ZS, it will synthesize a matching network, though it's not, I mean, we'll talk about making such matching networks, but it's not very complicated to design the matching networks on the source and load side to get this, right? And the other thing that this is doing is it's objectively telling you that this is the best gain that you can get, right? So it's also telling you that you're doing as well as you can do and nothing more. Does it make sense? Challenge here is that we need to make sure that we, in addition to that, those optimum source and load impedances exist, right? We also, I mean, as for an, when I say exist, for example, it might turn out that the optimum source impedance that you see is an additive resistance, or the optimum load impedance that you see is an additive resistance, right? And those are the situations where you cannot, in a real term, go from your source uh, and synthesize a matching network that creates that negative resistance, right? That you cannot do. So as long as it exists, though, you can create these networks. But one of the other constraints that we place on ourselves is this network going to be stable, right? We asked ourselves, is the amplifier going to be stable, right? And by stability, there are many ways to look at it, right? But if we want to be very safe, we can define this concept of what we call unconditional stability. And what does unconditional stability mean? Unconditional stability basically says that no matter what load, so I have this 2-port over here, right? No matter what load you connect here, right? And no matter what source impedance you drive the port with, right? There is no scenario under which you basically create a scenario where you have a gamma in, right? That is gamma in is always less than 1, and gamma out is always less than 1 magnitude if gamma s and is less than 1 and gamma L absolute value is less than 1, right? This is basically what you are trying to achieve. Or another way to think about it is that sure, you are going to work with only a known Z load, right? You are going to drive only a known Z load, but it is highly possible that due to some variations or in some situations, your Z load changes and some other load is presented. Or if you are a transistor designer, you don't know what load people are going to present to it, right? But you decide that what you would like is a situation where no matter what load is presented and no matter what source is presented, you will always find that, remember, looking in here, this was a function of what gamma L was, and looking in here, this was a function of what gamma S was, right? The impedance that you see. So no matter what, as long as the gamma S absolute value is less than 1, what we are saying is that the absolute value of gamma out is less than 1. And similarly, we are saying the absolute value of gamma in is lesser than 1, no matter what load impedance that we apply. So this is a stability condition, right? And what we can show is that in order to achieve this stability, there's of course any way to check, right? One thing you can do is you can apply all positive loads and look at gamma in, apply all, so you can do a brute force check, right? By varying gamma source and gamma load, right? Or effectively, this is basically saying that you vary ZS and ZL, right? And then you keep checking to see whether gamma in absolute value is less than 1 and gamma out absolute value is less than 1, right? You check if these are true. So this is one way of verifying if things are okay, right? But there is also, there are these concepts of stability where you can basically show that there is what we call the Rowlett stability factor, right, which is usually represented as K, and that is 1 plus delta squared. Remember, delta was S1 1 S22 minus S21 S12 minus S11 squared minus S22 squared, right, divided by 2 S12 S21, right. This is called the stability factor, and remember we said delta was S11 S22 minus S12 S21, right. So you first compute these two parameters and then you check if K is greater than 1 and delta's absolute value is less than 1, right. Then if these two conditions are satisfied, then you are unconditionally stable. Right. So now we have added another step to our amplifier design, right. So we take our transistor and we first make sure that K is greater than 1, delta is less than 1, right, and we know that things are going to be unconditionally stable. Then we can go back to what we did before, which is we can design the matching network with gamma in and gamma out optimum, and we basically have accomplished the gain. Now in there is, so the important thing to note, by the way, with this K factor and delta test, right, is that larger K doesn't necessarily mean more stability. Okay. Whereas there is another test which we call the mu factor test, or it's called the Edward-Sinsky stability factor, right, and this is mu, and mu is 1 minus S11 squared divided by S22 minus S11. Okay, and if your mu is greater than 1, right, then it's stable, and if your mu is higher, you are more stable. Okay, so this both of these approaches are sort of equivalent, right, but the good part is most simulators will give you these factors right away and you don't have to calculate them out by yourself, right, but it's important to know what they mean. But effectively what from a design perspective, then I take my two-port model of my transistor, right, I have the S parameter model of my transistor, then I can first check if it's unconditionally stable, right, and then design for optimum ZS and ZL, or actually I should, design by using matching networks. Let's look at that question this way, right? So you have a two-port, right? You are interested in, this is, let's say, just your transistor, right? And now you are worried about whether this two port is stable or not, and you see that it's not unconditionally stable. So there exists possibly some source or some load, right, which will basically make it unstable, right? Right? There exists one of the two that's possible. So what now you have a situation is that you say that's okay, it's very close, but you design some sort of matching network because you know what you are trying to match to, right? So you have some network, and now this is what is exposed to the outside world, right? For practical purposes, now this is your two port, right? And if this two port is unconditionally stable, then that's fine, right? Because now no matter what load and what source is presented to you, it's stable, right? So this is okay, but it's a risky way of doing it just to rely on the matching network, because then you have to be very confident in the loss model of your matching network, right? So more traditionally, what people will do is they will add some loss that is intrinsic to the device itself, right, to make sure that it becomes unconditionally stable, and then design the matching network. Because what you are trying to solve for is a situation where if everything works exactly like you planned, if the source is what you want, the matching network is what you want, your load is what you want, then things might be okay, right? But you are trying to, in practice, design for a situation where it isn't that way. So for example, if you're designing this as a power amplifier and it's connected to the antenna, right? Then when a hand comes close to the antenna impedance changes. And so the matching network now is no longer providing optimum, it's providing some other network. So that's the design problem. That is the concept of conditional stability and the concept of stability circles. Right? When we say on the two port, right? When we say on the two port that I am looking in over here and I'm seeing gamma in, right? And I'm terminated in some ZL, right? And I'm looking over here and I see some gamma out, right? If I just remember, my condition for stability, unconditional stability is absolute value of gamma in is always lesser than 1. Or basically I'm saying that S11 minus S12 S21 gamma L divided by 1 minus S22 gamma L, right? This absolute value is less than 1, right? This is what I'm saying. And what I am trying to say, my objective is that no matter what gamma L is, that this is true, right? And gamma L is ZL minus Z naught divided by ZL plus Z naught, right? It's basically ZL normalized to this. So as you keep changing ZL, gamma L is going to change. So ZL, you can think about so ZL is some RL plus JHL, right? And I am constraining basically that RL can go from 0 to infinity, JHL can go from minus infinity to plus infinity, right? So this is the entire possibility of ZL. So no matter what ZL and no matter what gamma L, this condition is satisfied, right? So this is on the input side, and I can similarly define a condition on the output side that I want gamma out lesser than 1. So this basically implies I want S22 plus S12 S21 gamma S divided by 1 minus S11 gamma S, right? I need this to be less than 1, right? And again, gamma S, I'm defining it as ZS minus Z naught divided by ZS plus Z naught, and ZS I'm defining as RH plus J times XS. RS again goes from 0 to infinity, Hs can go from minus infinity to plus infinity, right? So now the question is, well, you are designing you're over designing the system, because you're saying that RL plus JHL can be any of this, and RH plus JHS can be any of this. What if I decide that I can basically constrain my system, right? I can say that my RL can only go from some R min L to some R max L, right? And my HL can only go from some H min L to H max L, right? So I am constraining my region where I think my ZL can be. Similarly, I can constrain my ZS region, right? And once I constrain this region, then I may be happy if these conditions are satisfied for all of the resistances and reactances that exist within that set, right? So this is conditional stability. My two-port is not stable for any of these, for this whole set, but there exists some set for which it is stable, right? So from a design perspective now, there is a nice way to visualize this, right? That what you basically can do is, you, for example, if you say that, okay, you apply the constraint that gamma in absolute value is 1. Remember, I wanted absolute value of gamma in to be less than 1, right? For stability. Now I am trying to examine what happens if I equate this to 1, right? So when I equate this to 1, I basically am saying that absolute value of S11 plus S12 S21 times gamma L divided by 1 minus S22 gamma L is equal to 1, right? So what are the set of gamma L? Again, gamma L is ZL minus Z0 divided by ZL plus Z0, right? This is a one-to-one mapping function. So, you know, as we keep designing, we forget thinking about ZL and we just think about gamma L because it's a one-to-one mapping function. But what we are trying to say is, what is the set of ZL, or what is the locus of gamma L, which basically makes this equal to 1, right? And what you effectively can show is that this basically, these are circles, okay? So these are circles where this center point, the center point, I mean, you can actually find all of these in literature, but it's basically a function of S22, S11 and the delta of your determinant of your transfer function of your S parameters, and similarly there is a radius associated with it, okay? But effectively, if this is the set of impedances, right, that is going to give you this condition, right, then it may be true that all impedances inside this region are gamma in less than 1, or all impedances outside this region are gamma in less than 1. One of the two, either this could be gamma in less than 1, or this could be gamma in greater than 1, right? So you don't know whether the regions inside are stable or outside are stable. But what you can do is, you can just take the center point, right, and run the S parameters, run this equation. You can calculate the absolute value of gamma in for the center point. If it is less than 1, that means the inside region is stable. If it is greater than 1, that means the outside region is stable. So you can just run a simple 1-point test. But regardless, either the region outside or the region inside, all impedances are going to guarantee this condition, okay? So then from a design perspective, right, let's say that you know that your load is going to be something, right? and let's mark that load. Let's say that the inside region is stable, and let's say that your load is over here. Then you think, okay, maybe I have some margin. If your load is over here, right, then that isn't a good condition situation, because just a small shift would move you outside the stable region. So from a design perspective, you can, I mean, if your load is over here and there is a very large radius over here, you have a lot of margin in your design. So you can design for conditionally stable systems. The challenge though is that this also means that you are capturing the full S parameters of your network. So it cannot be true that there is some leakage model in your system where you have your two port for which the S parameters has been characterized. You decide that I'll basically have my matching network and my matching network, right? But it turns out that there is some coupling between your matching networks here, right? That's effectively changing the S parameters of this system and maybe changing the center and radius of these circles. So you run the risk that there is a possible situation where this gets unstable.
Also, things, the load can vary with respect to
Process, frequency, temperature, all of those are possible. So you can design conditionally stable systems, particularly if the radius is very large, right? And you can basically in the case of the source stability, so this gamma L, the radius is basically going to be proportional to 1 over S22 squared minus delta squared, okay? So if you basically have a situation where this is a large number, right, then you can design provided the inner region is stable. If it turns out that the outer region is stable, then you need the resistance to be actually small, radius to be actually small, right? So designing unconditionally stable systems is done, just has to be done very carefully to make sure that you are aware of what your actual ZS is and where it lies inside your source and stability circle. So a similar concept exists on the load side, and you design for it. Borderline, yes, but usually you try to get in design in ICs KF greater than 1 because you're always worried about parasitic coupling scenarios that you're not confident in. And typically, while you may know the drive impedance that you have, when you are starting to design a block, it is not that you know what the interconnect between your block and the other block is going to look like. And you can of course define it all to be 50 ohms or whatever ohms Z0 that you choose on chip, but there will always be slight changes that happen when you actually simulate. So it's a bit risky. So typically we stabilize and make sure that KF is greater than 1. These circles are obtained at a given frequency. So each of these circles exists for each frequency. So if you're designing across frequency, then it is true that your load will move, the load that you're designing for is going to move, the center is going to move, and the radius of the circle is going to move. So you have to track it at all the frequencies that you're designing at. Yes. Brilliant. So to just maybe review what we have looked at, we basically see that we need to do conjugate match to maximize power transfer, right? So there is a gamma S maths for power transfer, for power gain, right? And then design matching networks gamma S to gamma S op, gamma S mats, gamma L to gamma L mats, right? And you can basically have gain your transistor and then check for stability, right? So you have the K factor and the determinant, right, with the delta, right? And then you have the mu factor. So if you follow this sort of recipe, right, you can design a fairly optimal amplifier uh, uh, once the S parameters of the devices are available. However, in integrated design, the one thing is that we have a very large array of devices available. We have a very large array of bias currents, bias points that are available. So the question then becomes, how do I design my amplifier, or how do I pick my transistor size, how do I pick my transistor bias point such that I maximize the gain, assuming that I do all this, right? So that's the next step of the process. But uh, before we go there, I think maybe we can actually I should also just add a note here that says that larger mu is more stability, right? So we can take a 5-minute break now, and we can then discuss with the transistor's performance and how to pick transistor in order to get the best gain possible from it.